For today's lesson, we are going to be covering Riemann surfaces. While this is a new term, we have actually encountered Riemann surfaces already. As part of our lecture on elliptic curves, we saw that an elliptic curve can be realized as the complex numbers modulo a lattice. And from that point of view, we geometrically saw that it can be identified with a torus. Now, that torus is an example of a Riemann surface. We also saw at the start of our lecture on elliptic curves projective n space, and we studied the projective complex line. So this is P1 of C. That is another example of a Riemann surface. And so today we're going to discuss the definition, see examples, and the idea for this video specifically is to introduce these notions, but in our synchronous lesson we are going to go into more detail and do examples together. And so this is just to motivate the ideas that we will encounter as part of our synchronous lecture. So as a recap, in our lesson on elliptic curves, we had various formulas and equations that popped up in our historical coverage to motivate the modern definition of elliptic curve. And one of the things that we saw is the following bijection. If we consider the complex numbers modulo a lattice, then we have a bijection between here and E of C. And E of C here is viewed as the points x, y in C2, such that x, y satisfy y squared is equal to this quartic equation. And the bijection is attained by taking z modulo the lattice and mapping this to x, y, where x is Sn z and y is Sn prime of z. And here, Sn z is the Jacobi elliptic function that was mentioned in that lesson. But we also saw that from the quartic equation we have a bijection to an elliptic curve, but we now have this point at infinity from where the identity of y squared is equal to the quartic equation, where that identity maps to. And so here we have the statement of what happens if we didn't want to go to the quartic and just wanted to go directly from the complex numbers modulo a lattice to the elliptic curve given by y squared is equal to a cubic equation. If we follow the maps, we end up getting this explicit function where we take an element z in the complex numbers modulo the lattice and map it to this capital X, capital Y, where now there's going to be a new function. This is known as pay of z and pay prime of z. But we are not going to be studying this in detail, so this is just to motivate that we can construct these isomorphisms and bypass discussing the y squared is equal to a quartic. And so what I want us to focus now is that realization that an elliptic curve is a torus. So how do we go about showing that? And so the way that this goes, and in many ways it's just putting rigorously the notions that we discussed on our lecture on elliptic curves. So we have our function that takes the set of points E of C, and so this is just the collection of x, y that satisfy y squared is equal to this cubic, but then we also have the point at infinity. And we have a way of mapping a point x, y to a point that is in C mod the lattice. And now what we are going to do is show that C mod the lattice can be identified with a torus. And so the torus is down here. And so the first intermediary step is to go from the elements inside C mod the lattice. And so keep in mind that since we are quotienting out by the lattice, we are working with equivalence classes, but as part of our discussion, we can restrict our attention to those m and n's where m is between 0 and 1 and n is between 0 and 1. And so here's a visual depiction. We have our omega 1 in the complex plane. So here the traditional x-axis is being viewed as the real axis, and the traditional y-axis is being viewed as the imaginary axis. So we have our omega 1, we have our omega 2, and we are interpreting C modulo the lattice as just this, all the points inside this quadrilateral, and including the boundary. But we are identifying points. And so now we can take m to just be between 0, specifically 0 less than or equal to m, and m is strictly less than 1. And similarly for n is greater than or equal to 0, but strictly less than 1. And now, under this identification, we would have that if we plug in 0, 0, we would get back just the origin. If we wanted to get a point along, say, in the middle, we can take, say, 1/2 times omega 1, and so that will get us over to this point here, and then take 1/2 n omega 2, which will then make us go up just half the length of omega 2. And then this point over here will correspond to 1/2 omega 1 plus 1/2 omega 2. And now what we are going to do is map the points inside the complex numbers modulo the lattice to this set here, which is the Cartesian product of the real numbers modulo the integers Cartesian product with itself. And all that we are going to do is send the entries m and n to the pair m, n in R2. And so the same m and n, so they're going to be between, it's going to have 0 less than or equal to m, less than 1, 0 less than or equal to n, less than 1. And now, let's go ahead and send the elements in this set. And the main thing is we have a bijection coming down here. This is also going to be a bijection. And now we're going to have a third bijection, which is that to a torus, which we denote by T2 of R. And so these are the triples, U, V, W in R3, such that U, V, and W satisfy the equation of a torus. And that's given here. And so you could use a 3D graphing software, plug this in, and you'll see that this gives you back a torus. And so we have the square root of u squared plus v squared minus rho, and then the whole quantity squared, and then we have plus w squared. And then that will be equal to 1. But how is the map from here to here defined? We have, of course, UVWs, and we have a rho here. What are these? Because the map going from z modulo the lattice to this here, that is easy. We can just send m and n to mn. And that's it. We got a bijection. But if we keep track of everything, we come back to c modulo the lattice, and we can view m and n in the following way. And so m and n, of course, are real numbers, but we can view them as in the following manner. So m can be realized that this is equal to the imaginary part of z over omega 2 over the imaginary part of omega 1 over omega 2. And now that z corresponds to the original element that we had up here in the lattice, and so that is m omega 1 plus n omega 2. So that's how we're mapping these elements. And so upon realizing m and n in this way, we then do the following clever trick. We want to now write these two real numbers in terms of inverse tangent, but specifically with a 1 over 2 pi in front of the inverse tangent. And so we can then realize this as w as 1 over 2 pi tangent inverse of some w over the square root of u squared plus v squared minus rho, and then the n can be realized as 1 over 2 pi tangent inverse of v over u. And once we have it in this form, we have our map. And so we can take m and n, viewed in this manner, and we map it to rho plus cosine 2 pi m times cosine 2 pi n, and then similarly for v and w as given here. And this ends up giving us a bijection between our original elliptic curve and the torus. So what are these notations in here? Because this is the equation of a torus, but this is usually not covered in our undergraduate curriculum unless you take, say, a course in differential geometry. So in this notation, this rho is the distance from the center of the torus to the center of the tube in the torus. And the 1 here is saying that the radius of this circular cross-section in the torus is 1. And so now we have that in the elliptic curve, under these bijections is in fact a torus. And so now we want to ask, can we draw other surfaces? So we just got a torus through this identification. Can we get others? And the answer is yes. So here is an example of what is known as the Riemann sphere. We also have a 3-hole donut. And so these are examples of Riemann surfaces. And a way of studying Riemann surfaces is by the number of holes that these n-hole donuts have. And so we're going to specifically be looking at what are known as compact Riemann surfaces. And so in that situation, we have that the sphere is an example of a compact Riemann surface, and it has 0 holes. The torus has 1 hole. This here has 3 holes. And we're going to be calling that number of holes the genus of the Riemann surface. So here is the technical and precise definition for what is known as a compact connected Riemann surface. We are not going to be using this definition for the summer, but this is here just to emphasize how to rigorously define this. So a compact Riemann surface can be viewed from the language of differential geometry as a complex manifold, but specifically a complex manifold of dimension 1. And so we have some open cover, there's going to be an atlas, and it has these topological properties, but again, we're not going to be worried about these terms, so if you have not seen these, do not worry. What we are going to do instead is use the following classification, and through that classification, that is how we are going to perceive Riemann surfaces for the summer. And then we are going to build the necessary tools and terminology that we will need for the various research projects from these. And so we have specifically the uniformization theorem, and that is what classifies what are known as compact connected Riemann surfaces, but specifically simply connected Riemann surfaces. And so the statement is that if we have a compact simply connected Riemann surface, then it is going to be it's going to be one of 3 different possibilities. So it's going to be spherical, in which case it has genus 0, it has no holes. And it turns out that in this case, it actually is just P1 of C, the same P1 of C that we saw at the start of our lesson on elliptic curves. And so we're going to see a demonstration of this, but as part of your assignment, you will actually be proving explicitly that P1C is in fact is in fact bijective to S2 of R, the Riemann sphere that is presented in this slide. The other possibility in the uniformization theorem is that the Riemann surface is Euclidean. And in this case, we have a donut, a torus. And so that's the case when we have genus 1 hole. And so in this case, it's a torus. And so elliptic curves are an example of Riemann surfaces of genus 1. We also have the situation where it is hyperbolic. In this case, the surface will have a genus greater than 1, and if we try to visualize it, it would look like this. And it's going to have it's going to be an n-hole donut where n is greater than 1. And it turns out that we can realize such hyperbolic Riemann surfaces as gamma mod h star. And so we're going to be introducing this notation in more detail as part of our synchronous session. But for now, we're just going to leave this here and we'll discuss this further. But the main thing is that we have gamma and it's a subgroup of PSL2R, and gamma will be acting on this set here h star, which is defined as the upper half plane. And so these are the points that we have seen in the problem sets from last week. So this is the points x plus iy in the complex numbers such that y is a real number greater than 0. And so we have xy real numbers, y greater than 0. But the takeaway is that all these Riemann surfaces have embeddings into R3, because a sphere, we can view it inside R3. A torus, we can view it inside R3. An n-hole donut, we can also view it inside R3. So let us look at the Riemann sphere. So for the Riemann sphere, So we have our P1C that we studied, and I'm going to write this as the complex numbers union infinity. And so this is just an abusive notation, but that's going to be the standard notation we'll use with P1C. And so we saw, as part of at the start of our lesson on elliptic curves, that P1C can be viewed as the collection of points x colon 1, such that x is in the complex numbers, union a point at infinity, which we denote by 1 colon 0. And so now what we are going to do is identify this with the complex numbers, and we're going to identify this with infinity. And so we can just write P1C as C union infinity. And so whenever we write infinity, that's just the point at infinity, 1, 0. If we write some complex number x, we really are saying x colon 1. Now the Riemann sphere is just the unit sphere in R3. So we have the set of points u, v, w in R3 that satisfy the equation u squared plus v squared plus w squared is equal to 1. And then we have the following proposition that gives us a bijection between P1C and the Riemann sphere. And so specifically we have a one-to-one correspondence between the points on the extended complex line, which is another word for the complex numbers union infinity, or P1C, and the points on the unit sphere. And this is what is known as stereographic projection. And so for this map, we actually have the bijection is listed here. And so let's unpack how this map works. And so the way that this map is being defined is that we can take some x inside P1C. So let's take some x in P1C. And we're going to map that x to the following element in the unit sphere. We're going to take x and then map that to the x coordinate, the following x coordinate, so twice the real part of x, over the modulus of x quantity squared plus 1. Now keep in mind, x is in C, and if x is in C, then we can define the modulus of x as the distance to the origin. So this is going to be u squared, actually let's not use u, let's use alpha squared plus beta squared, where we're writing x as equal to alpha plus I beta, for alpha and beta being real numbers. And similarly, we can then send x to the following y-coordinate in the unit sphere, so twice the imaginary part of x, over the modulus of x quantity squared plus 1 we take, and then finally the z-coordinate would be this quantity here. But if we wanted to go in reverse, so if we had a point on the Riemann sphere, it turns out that the inverse to the function we just defined going in this direction is attained by taking u, v, w, a point on the unit sphere, and mapping this to this point here, u plus iv over 1 minus w. And this here will define a bijection between P1C and the unit sphere. And so let us do a quick visualization of this mapping. And as part of our synchronous session, we'll go into more detail. But the way that stereographic projection, this mapping that we just looked at, the way we can interpret it is we're considering a fixed point, say the North Pole, and we're drawing a line from the North Pole, and it's going to intersect some point on the sphere. And so we're going to have some point intersection with the sphere, but then if we have the sphere positioned in such a way that this here, this plane, is in fact a complex plane, then we will get back that this line will intersect the plane. And so this point here in the complex plane, that is our x. This point of intersection of the line that connects this point to the North Pole, that point in the sphere that is not the North Pole that we have as an intersection, that is our UVW. And so we have a nice visualization for this mapping. Let us now briefly revisit elliptic curves. And so this is an example of a Riemann surface. We just saw in our earlier slide that we have a way of going from our elliptic curve to a torus. But in that definition, there was this mysterious pay function, this symbol here, pay. And the way that it's defined, and this is just, again, just putting this for motivation and historical purposes, we are not going to be using these formulas, is that this Weierstrass pay function is a function from the complex numbers modulo the lattice to P1c, where it's defined in the following way. Pay of z is 4 times 1 over z squared plus, and then we're just summing over all the elements in the lattice minus the origin. And so we just sum over these values. And so this ends up being a doubly periodic function, namely pay of lambda z plus omega is equal to pay of z for every omega in lambda. And in this manner, the coefficients in the elliptic curve, this a and b that we had earlier, we can realize them as elements that can be attained from summing over lattice points. And so viewing it from that perspective, if we come back to our elliptic curve, now we just have that the elliptic curve depends on the lattice. And we'll discuss this in further detail in our synchronous session. But the main thing is, this is just to make these maps explicit and explain where the Weierstrass pay function was coming in. But we still have our maps. We go to the complex numbers modulo the lattice. We go to the real numbers mod z Cartesian product with itself, and then the torus. For our last example for today, we're going to consider the case where we have a Riemann surface that is hyperbolic, that is, the genus is greater than 1. But I am going to focus on this portion over here that I just skimmed over earlier. And so we have that such Riemann surfaces arise as gamma mod h star. But what is gamma? What is h star? Well, let's go ahead and discuss this. So we need some terminology first. So let's go ahead and define D to be the unit disk. And so these are all the points in the complex plane that are at most a distance 1 from the origin. And so that's the unit disk. We have H2. So we have already encountered this as part of our problem sets from last week. So these are all the points in the complex plane such that the imaginary part of tau is greater than 0. But we also have the extended upper half plane, which is the notation that we just saw in the previous slide. And that is defined as h star, where h star is equal to h2 union q union a point at infinity. Another way of writing this is as h2 union p1 of q, because p1 of q can be identified with q and some point at infinity. And so that is what is known as the extended upper half plane. Now, PSL2R is related to what we have seen in the problem set. So last week you were introduced to the special linear group of degree 2, and that was a collection of 2 by 2 matrices that had determinant equal to 1. Well, PSL2R is just going to be PSL2R modulo the center of PSL2R. And in this case, it happens that the center of SL2R is just plus or minus the identity. And so we are just modding out SL2R by the identity. And so just keep that in mind. So PSL2R is just SL2R modulo plus or minus the 2 by 2 identity matrix. And so matrices in this quotient group are identified with their negative. And we say that a group gamma with binary operation circle is a Fuchsian group if it is a subgroup of PSL2R and we have the following property holds. That G sub tau, where now G sub tau is defined to be the set of matrices A, B, C, D. Notice this plus or minus, and that's coming from the following. We're working with subgroups of PSL2R, so matrices are identified with their negative. So A, B, C, D and its negative are essentially viewed as the same element inside PSL2R because we're looking at this as a quotient group. And so we are looking at so G tau is the collection of all matrices such that A tau plus B is over C tau plus D is equal to tau. And this here is going to be finite for every tau in the extended upper half plane. And so we will discuss tomorrow where this terminology is coming from. And so our focus is only on those Fuchsian groups gamma, which are torsion free. That is, if we have an element that has a finite order, so a to the n is equal to plus or minus the identity, then it must be that that element is in fact the 2 by 2 identity matrix, or it's negative, which we are identifying it with itself. And so what we are going to be investigating in our synchronous lesson is this set, gamma mod h star. And so this is going to be a set of equivalence classes such that tau is an h star, but each of these equivalence classes is defined in this way. And so we'll discuss this in our synchronous session. But the main thing is that we have these maps. And so we can take H2, map this bijectively to the unit disk, and then we can map this bijectively to this S plus, and now this S plus is going to be our corresponding Riemann surface. And so we have these maps. And so again, we'll discuss this in further detail in our synchronous session. This is just to introduce the ideas of what we will be discussing. And so that finishes for this video, but in our synchronous session, we'll go into further detail and work through some examples and prove some neat results.